Coimbatore. Now I will hand over the sessions to Dr. Rajesh sir. Okay, sir, you can carry.
And thank you, sir. I'd like to welcome everyone for this session. And I'd like to thank Professor Karnakaran for giving me this opportunity. And like today, the topic that I'm going to discuss is about some of the novel applications of additive manufacturing. And under the circumstance, like it is not that I'm sharing any videos or I mean I'm sharing a description video, but other than that, much of the works that we are going to discuss today is completely the work undergone by me and my colleagues, um, or my research scholars and my PhD candidates who worked along with me. So it is completely the case studies that we have did at CIT and in our center of excellence. So having said that, like what we do at CIT as a research focus is like we take two different technologies. One is the supply chain management, and the other one is the additive manufacturing. What we do is we take two domains, we try to integrate both these two domains, and integrating these two domains, we can explore into many areas or many products could be explored. But in our research group, we don't explore into much of the other areas. We specifically concentrate on healthcare. Healthcare is the domain that we concentrate. And again, within supply chain, there are many areas that we could explore, but our exploration is limited to areas like low cost, inventory management, lead time reduction, undergoing lean, and how we can achieve agility or responsiveness. That is the specific focus that we have from the supply chain perspective. And from 3D printing perspective, it is on customization, how we can go for manufacturing very complex profiles, high accurate parts, and how we can go for reducing the lead time of products. So these are some of the major areas that we look in. And this particular area, I've been working since 2002, since the day that I started my PhD back in Loughborough in England. From that time onwards, I was exploring into this particular area. So that's a bit of a background on this. And we all know that, and I could see from the schedule that you might have learned or you're in the process of learning about additive manufacturing, the types of additive manufacturing techniques, the possible inputs that it could be given. But I'm concentrating on the application of it. So I'll just give a slight outline of what additive manufacturing is. So we all know that subtractive manufacturing, a process where we take a bulk of material and from the bulk we try to subtract what we need, well known as subtractive. On the other hand, we use additive manufacturing wherein you have material in major three different forms. One is the liquid form, the solid form, or the powder form, or the filament form. And using that, we tend to bond layer over layer. And in our specific application or whatever the exploration that we do in our center of excellence or in our research lab, we use two major machines. One is the Connex 260, which is from Stratasys. When we purchased in 2013, that was said to be world's seventh machine, and we were the first one in India to get that particular machine. Um, and we use a traditional FDM, and we use a couple of other accessories which goes along with that. So this is the machine that I'm speaking about. It's it's a polyjet technology, which is a Stratasys one, um, and I have a short descriptive video of what it does.
Photonics uses inkjet printing technology that can jet two materials at the same time. This allows you to produce models containing a whole range of material properties to represent your final product. Each layer of resin is just 16 microns thick. It can even mix two materials to create a whole selection of properties, such as this material, which is tough enough to simulate ABS-like engineering plastics in applications such as this, or even this, that can do this. With Objet's 3D printing technology, you can take your design idea and rapidly transform it into a functioning prototype. And you can do this with all the subtle details of your intended product built in, including the different material properties of assembled goods, such as this part. Multi-material technology is that you can build up to 14 different material properties, textures, and shades into a single part in a single print job. Objet has an incredible range of over 60 materials, from rubber to transparent to engineering and plastics, with the ability to mix and match various combinations.
Okay. One major advantage of this particular technology is I can, to say it in a simple way, we can say that it's a combination of stereolithography and SLS and a 3D printer. So that is where we can quickly describe of this technology. And it uses 8 different heads. And using 8 heads, we can come out with 154 material combinations. And when we say 154 combination, this is one example that we can put across. Like you can print glass-like polycarbonate parts, you can print ABS-based parts, and you can print rubber-like parts as well. And this is along with the support material which goes in between these layers. So this technology we used for our application, and that is what the entire focus of today's lecture is all about. How we use this, and what sort of novel or innovative products that we came out in healthcare domain. And primarily, this particular technology uses 2 major category of material. One is the primary material, the other one is secondary material. Let us say that we want to print a polycarbonate one, a glass-like structure. So, uh, like, excuse me, I think somebody's microphone is on. Could the person kindly switch off their microphone? Right. In terms of primary material, it is one single material wherein a part has been built. Like let us say, for example, ABS. ABS will be using as a primary material over here. And let us say that we want to combine ABS and rubber, and I need to print, make a part with a combination of ABS and rubber, like what we have seen over here. I want to print these 2 combinations together. Then this falls under the category of secondary material. And the third option is we can also go for digital material, wherein we can select the levels of elasticity, or we call it as the show hardness levels. In one rubber-like component, you can decide whether you want a 40D show hardness or 60D or 80D. What is the show hardness level that you want? It can be fixed up using the digital material combination. So these all 3 possibilities of can be done, and in total 154 different categories of or different types of materials can be printed. Some of the example products that it could be possibly built can be like what you print in a stereolithography can be done, what you print in an SLS can be done, wherein the accuracy levels it goes until 16 microns. And one thing which other technologies can't do is we can blend these 2 things. Usually we print the rubber-like part separate and then we put a glue in order to bond these 2. But here everything goes in one single print, and these 2 are printed together in one single go. So that is one of the major advantage of this particular technique. As I was mentioning to you, like my focus is on healthcare domain, and within healthcare there are very wide amount of products, and of the very wide range of products, I specifically concentrate on prosthesis. And again, within prosthesis, there are 2 major categories, which is the internal prosthesis and the external prosthesis. What internal prosthesis is? Anything that you put inside the body falls under the category of internal prosthesis, like metal parts which goes in, the titanium holdings which goes in, the scaffolds which goes in. All these fall under the category of internal prosthesis which goes inside the body. And anything that goes outside the body which is fitted over the body, that falls under the category of external prosthesis. And our focus is mainly on the external body parts. And looking at the case studies, today I'll take you through a couple of case studies. We'll see how the time permits, and based on that, we'll go through different case studies, starting from diabetic foot to laparoscopic surgery to dental aligners to clubfoot treatment and prosthesis for a peacock, and finally to how we brought in a novel way to treat bed ulcers. Right, starting with diabetic foot. We all know that the fourth leading cause of death is diabetes. And when I ask a question like how many of you know somebody or other, or somebody in your family who is diabetes, I'm sure that every one of us might know somebody, or that gives a very clear idea that diabetes is a very much prevailing disease, and India ranks very high in terms of diabetic population. And in future, about 2030, India is said to be, possibly it would be the leader for the issue of diabetes. And within Tamil Nadu, it's about 5.8 lakh people are having the severe diabetes, and this rate is growing up. And here, in terms of diabetes, they categorize into three major categories, and I'm speaking about the third level, which is the highest level of diabetes, which is 5.8 lakh. And every 20 seconds, a leg is lost because of diabetes. Or we might have heard that somebody saying that they have very severe sugar, and because of heavy sugar or diabetes, they lost a limb, or they lost a finger in their limb. It's all because of diabetes. So we might have heard about this. So that is why we thought we'll give a focus on. And looking at the scale across globe, yes, it is extending, and it could be found everywhere. So that is the situation. And across globe, by 2040, 642 million people are predicted to be with diabetes. So we decided that we'll try to come out with a product, or we'll do some research in terms of diabetes, and we'll see how additive manufacturing can be used in terms of treating diabetes. So that is where we started our research focus. And with that as a focus, we communicated with nearby hospitals in Coimbatore, and we had questionnaires. And for our research, we involved roughly about 2,570 respondents, of which the male population is 1,885 and rest of the female population. What we do is we tend to attend the frequent diabetic camps, and we tend to, some of our researchers, they go and they sit with the diabetologists, and for this particular project we worked with a couple of diabetologists, and then we came out with this particular product. So in our questionnaire, we were trying to explore how often a patient tend to meet a diabetologist, or how often they meet the general practitioner. So this was a stretch of data, and from this we could see very clearly, like roughly around 6 months is the average time that a patient meets a diabetologist or a doctor. And mostly of the population that we analyzed, roughly about 60% of the population, they meet a general practitioner rather going to the diabetologist itself. And our survey gave out very interesting facts, which I come to speak about it during our concluding session. But roughly about 50% of the respondents that we analyzed were above 56 years of age. And as I mentioned, only the 64% of population, they tend to meet the GP rather the diabetologist itself. And of the entire population that we went through, about 52% of the sample population faced foot-related problems and its allied complications. When I say foot-related problems, like then we try to explore what are the allied complications in terms of diabetes. So one is high blood pressure, foot problems, where the Then the combination of problems have been found: high blood pressure and foot problems, neuropathy and foot problems along with heart disease. So within diabetes, foot was found to be one of the common issue, irrespective of the level of complications that the patients faced. And as we specifically concentrating on food, and we try to explore how many of the respondents were aware that they would go to a situation of amputation if their foot is not being treated. And only 40%, 42% of the population were aware of it, while rest of them were not aware, and of which 10% are not at all completely aware of it. And again, we went back with the questionnaire like how many of the respondents know about a thing called customized insole? Because in additive manufacturing, our one of our major focus is how can we customize a product. So that is why we are looking at. So customization of something to put in the foot was our primary focus. So that is why we looked into this particular area. How can we customize, or how many of the respondents were aware that customization is a possibility? And only 43% were aware of it, while rest of them are not much aware of it. Fine. So what is that really is causing this foot amputation? That is where the question boils down. And when we speak about that, let us take a patient, and we might have heard from diabetic patients that early morning when they wake up from bed, they have a tingling sensation, or they have a burning sensation in their foot, or they don't have any sensation at all. So that is one thing which has been commonly seen or commonly heard from the diabetic patients. This situation occurs when they are in the mid stage of their diabetes. So what happens is we all, every one of us, no matter what will be the age, when we walk, we tend to create some specific pressure points. And these pressure points are located underneath our foot. I'll come back to it again. And these pressure points are located underneath our foot. And a person who is diabetic, when he loses his senses, the pressure points would definitely act as what it was acting earlier. And when these pressures are acting, when they are in the mobility state, automatically because of severe diabetes, their skin tends to become quite very soft. Like this is the blood flow level in the healthy person foot, whereas this you could see the blood flow levels of a person who is diabetic or a diabetic person's foot. So what happens is when a healthy person, the veins that tend to carry, or the nerves that are carrying blood, are quite strong, and they are right in their shape or right in their profiles. Whereas a person, the moment he becomes diabetic, his skin texture becomes very softer, and his veins starts getting more softer. So that means that the veins starts getting closed up because of the flexibility, highest amount of flexibility levels in the vein. When the vein starts getting closed up for a diabetic patient, but still his pressure point would be the same. And as the pressure point becomes more and more, the veins, it will start getting closed. This will, at a point of time, this will stop the blood flow that is happening in the foot. This will completely stop the blood flow. As the blood flow stops, we all know that the blood which comes to the bottom of the foot, it need to go back to the top of the head, but that doesn't happen. So some of the blood that gets stagnated, and we know that stagnated water is the one which causes much of odor, and it tends to create disease or some sort of germs in it. The same thing applies to human body as well. The stagnated blood which is left in the foot will start creating gangrene, and this gangrene, they need to clean it within a certain period of time, but left uncleaned, it would start spoiling the entire nerves which are down here, the fine nerves. And end of the day, when the situation comes to a place where they can't treat it, the only solution is they go for an amputation. So the initial state that it happens is as the pressure ulcer goes, and it will start creating wounds like this. And end of the day, After the wounds, the next solution, when they leave it untreated, that is where it goes for amputation. Fine. So this is a bit on the medical perspective, from the simplest medical perspective that we could go on. Now, many people would think, what is that a mechanical engineer has to do with over here? Um, right. Let us take a surface, and when it has been loaded, and when your point of contact is very less, it is obvious the friction rate would be very high, and the load distribution won't be proper. Now, for the same situation, if I'm increasing the surface area of contact at the bottom, obviously the load distribution would be better. This we all engineers would know about this, and this is a very common thing. And the same thing goes if a person is weighing about 90 kilos, and theoretically 45 kilos need to go to his left foot, 45 kilos of his weight need to go to the right foot. And when this distribution is proper, that means that the load distribution is okay. That is, we are speaking of this situation. But our foot doesn't distribute this load equally. What happens is there is a particular profile in our foot wherein, let us say, our entire surface area of foot about 10 centimeters square. The entire load doesn't get distributed to this 10 centimeter square area. It only gets distributed to a space of roughly about 3 or 4 centimeter square area. So it doesn't get distributed to the entire 10 centimeter square area. So one thing that is very clear is, if you are able to improve the surface area of contact, the load distribution is better. Number one. And number two is, as I mentioned, the foot profiles are different. So this completely gives a clear idea that the maximum loading tends to happen here, here, and some parts of here. So roughly about 40% of the foot only gets loaded. Rest of the foot, it doesn't get loaded. So that is where I mentioned that if we take our surface area of the foot is about 10 centimeter square area, just for example, only 40 centimeter, only 4 centimeter square area gets distributed with the load, while the rest doesn't take the load. So when the rest of the foot doesn't get loaded, it is very clear from our shoes. That is where the shoes wear rate are different for each one of us. Like the moment we see our shoes or our sandals that we are wearing regularly, we could see it's having a different wear rate at different parts. Theoretically, it shouldn't be the case. Like it should have worn equally everywhere. But in reality, that doesn't happen. That is because poor surface area of contact, and that leads to poor load distribution. So this is one thing which we could see. So then we went to the anatomy, like why is this happening? And that is where we all fall within these three categories. That is, either we would be having a flat foot, or we'll be having a normal arch, or we'll be having a high arch foot. Usually people who are very thin or who are athletes, they tend to have this high arch. So that's why it is called as athletic foot or high arch foot. On the other hand, most of us, we would be falling under this category of normal arch. And people who are quite bulky, or people, there would be some children who are born with flat foot, and throughout their lifetime they will have a flat foot. So that is one category, and these are the three major categories of foot. Like from our experience, when we went through these questionnaires, what we realized is we need to understand what is the type of foot, and then only we can get our foot fear. Any mismatch in foot, that is where it leads to um, uh, pains in the knees, or pain in the knee joints or the knuckle joints, which we tend to, when we are healthy, we don't feel this pain. But when we are crossing about 50 years of age, that is where all these issues happen. So next time, be careful when you are selecting your footwear. If you are a flat foot person, select soles which are very flat. If you are a normal arch person, the best sole for you would be something with a small heel, and only the high arch person can wear a high heel shoes. Anything of mismatch, then it would start creating an impact in terms of our foot. So that is one simple thought I thought I will share with you. So from this, we came to two major conclusions. One is surface area of contact is very essential for the load to be distributed. And second thing is the friction or wear rate, which is happening because of poor surface area of contact. And looking at people, we have two major types of activities. One is the static loading, and the other one is dynamic loading. When we stand, we fall under the static loading. When we jog, walk, run, all we fall under the category of dynamic loading. So our footwear need to take these two major types of loads. So that becomes an essentiality. So loading also started becoming as one of the essential parameter which need to be considered while we go for design of the footwear. And yes, like we have seen or we have heard that MCR or there are a number of brands which are there which claim to have uh, footwear. All it does is, or all it does as a custom footwear is, it just only provides a cushioning effect. It doesn't provide anything more than a cushioning effect. And even if we are trying to wear these, one of these kinds, we are not supposed to wear any of these soles more than 3 months, because the moment it loses its sponginess, it stops taking the load. Rather, it will start giving an adverse effect. So that is one thing that we noticed during our situation. And when we go for selecting our shoes, all that happens is our foot size is measured on only one parameter, that is what is the size of the foot. And that is the only parameter which has been measured. Theoretically, it shouldn't have been, because we need to map our footwear based on the type of foot that we are having. But that is one major missing factor which is found in existence. So these were some of the parameters that we observed when we started getting into the research type. And I was speaking about customization. Like if we take a bunch of population, like let us say this person, let us say her foot size is 7, and this person, her foot size is also 7, and this person, her foot size is also 7. But all these three different people will definitely have different type of activity, and that means that the footwear is not matched for them, because she might have a flat foot, she might have maybe an athletic foot, she might have a normal foot, but these are not been considered. Even for one person, it is not been considered. That is what our survey revealed. On top of it, from the time that we grow, uh, born to the elderly period, somewhere at this stage we attain a proper footwear size. Maybe let us say that this person will attain a footwear size of 8 during this stage. And this 8 remains the same throughout his lifetime, but his activities varies from time to time. But this has not been considered at the moment. So these were some of the specific focuses that we got when we were doing a research. Even if we consider for one person, we are not able to map it, then that means that we haven't anything much for the entire population. So that is where the focus was. So this clearly gave us four major areas to concentrate: static and dynamic loading activities, surface area of contact, how can we reduce the irregular wear rate, and how can we improve customization based on the type of activity that they are going, or according to the profile of the foot. So these are some of the areas that we thought we need to specifically look in. Fine. People would think like, fine, when my grandfather was working around, or when he is around, like he never bothered about all these factors, and why is that we are learning or we are hearing all these new terminologies which doesn't add much to it. He was comfortable, he was working, and he is playing his role, but he never bothered for any custom footwear. Why is that we are hearing about this? Right. We did happen to go for that as well. And then we realized that most of them, they were from the farming, or in the early days, they were on farming. And when they are in farming, they tend to walk barefoot. And these were the surfaces that they walked in. And if we look at it clearly, the profile underneath, it tends to change. The surface underneath, it tends to change according to the profile of the foot. So that means that the surface area of contact over the surface where he was walking was 100% intact. But whereas the surface area of contact that we are walking or is not the profile that what is supposed to be. So we can't change the surface area, but we need to change our footwear. So that boils down the answer to it. That is, earlier they were having 100% surface area of contact. The load distribution was proper, and that means that as the load distribution is proper, that is, means very clearly a sort of there was a customization, but the customization was done by the ground to the foot. But here we can't. We need to find a way how we can do it. So that is where we decided, okay, we need to come out with some novel idea. So moving to gauge cycle, like gauge cycle is one thing, like when we are born, and by the time of 5 years, every one of us tend to get a pattern of walking. That pattern of walking is called as gait cycle. Like some of us tend to lean towards the left and walk, some of us tend to lean towards right and walk. So that is called as a gait pattern. And it is very much necessary to understand the gait pattern when you are designing the footwear, because any mishap in the gait cycle will start creating issues in terms of your will start bringing orthotic issues to the patient or to the person who is wearing this footwear. So we make sure, or that we are sticking to this gauge cycle, and we are 100% making a complete custom insole or custom sole for the patient. And looking at the gauge cycle, when we walk, only for 60% of the time our foot is in contact, whereas rest 40% of the time our foot is on stance or in swing phase. So these are some of the parameters which was been taken into consideration, and then we start mapping it. Ideally, what we did is we took different types of foot and we started understanding the pressure distribution under the foot. I'll tell you how we did it. Like we take the patients and we make them to walk on this EMED sensor. This is the sensing platform, wherein when you walk on it, it tends to clearly understand according to your body weight, according to the person's type of gauge cycle, it tends to map the pressure points. And for those pressure points, we tend to um, go for production of the custom insole. So we measure the foot size as like the traditional method, and then we make them to walk on the platform. And once they walk on this platform, then we try to map the pressure points. We see where and how the load is being distributed. And from understanding the load distribution and understanding the gauge cycle, you can see a fine line which is going on. This is nothing but the gauge cycle, and we map the gauge cycle at first. And once after giving the patient a custom insole, we make the patient to wear the same custom insole and make them to walk on this platform, and we make sure this gait line and the gait line that they have after wearing a custom insole both are aligned to the same. So it is 100% customization that what we try to do. So this is a detailed picture of it. Here I have taken two different arches. One is the high arch and one is the normal arch. Looking at the normal arch, you can see theoretically the entire area need to be loaded, but that is not happening. This pink region are nothing but these are the regions where the very high pressures are there, and red regions are the second very high pressures, and then goes like yellow, green, there's light blue, dark blue, and black are the areas where there is a less amount of contact, and you can see much of the surface area of contact is not there at all. The idea is very simple. Wherever the high pressures are there, we tend to offload the pressures in high pressure zone, and wherever there is no pressure at all, we try to load those regions with pressure. So that means that we are trying to distribute the pressure through the foot, and by distributing the pressure through the foot, we also make sure we are improving the surface area of contact of the foot. So that is what we are trying to do with this particular project. So we take the patient, we map him, and then we also measure the arch height, wherein after measuring the arch height, we split the sole into 5 different zones, and based on different zones, we try to 3D print it. I was mentioning to you about when I was speaking about the 3D printer, like in this 3D printer, we can change the elasticity levels. So that is what I was mentioning. So here, let's say, for example, in this particular sole, you could find small slices of segregation. Like if the highest pressure is here, this point would be with show hardness of 40, wherein that is the cushioning effect will be more, and this region will have a show hardness of 60. That means it will have a lesser amount of cushioning effect. So now we are speaking of the load being distributed by varying the elasticity levels, and the load has been distributed, and you can find the surface area of contact has been increased. So this has been printed through the 3D printer, and this is the completely customized insole for one person for his existing weight. We tend to completely 3D print a part. And after printing it, this is an analysis of how the pressure distribution have taken place in the for a normal foot person. Like this is when a person with barefoot, these dark ones are with the person with barefoot, and the gray ones after wearing a custom insole. You could find that the higher he had a pressure of about 70 kilopascals, which has been reduced to 49, and 81 kilopascals has been increased to 124. That means that somewhere for this person, the pressure distribution we have varied from region to region. And if you look at it, there is one region where there wasn't any pressure at all, and suddenly a 54 kilopascals has been distributed to this particular place. That means that the surface area of contact have been increased. And we didn't stop there itself. We also went back um, to understand the traditional practice of how it is done in Ayurveda. And in Ayurveda, like even if you do a Google search, you will find all these details. Like we all know that for insulin production, pancreas plays a major role, and the nerve endings of pancreas lie in the arch region of the foot. And with our custom way of with our regular way of our footwear, we don't load this pancreas areas at all. There is no contact in this pancreas area at all. That is, the arch region doesn't have any contact at all. So that means that the nerves over here never gets activated. So that stops, or that literally makes the pancreas to functionality less, obviously leads to poor insulin production. So we also analyzed it from the other perspective, and we came to a conclusion that our research is going well on its direction. And this is the load distribution before and after. You can see the performance of normal foot patient as compared to um, with and without custom footwear. So this gave a clear idea in terms of pressure distribution. And in terms of surface area of contact, yes, we varied the surface area of contact, wherein earlier the surface area of contact was 135 square centimeter, and now it had an increase of roughly about 14.5%. The area of contact also got increased. I'll just quickly go through. And this is before and after. Here we can see the surface area of contact has been increased, and the peak pressure region over here that has been offloaded, the peak pressures have been offloaded. So this is one product that we came out using completely 3D printing, and we did analyze for both the right sole and left sole, and this is the entire spectrum of distribution. On an average, roughly about 32% of weight has been distributed, or pressure has been distributed. And once we say pressure distribution and improving the surface area of contact, that means that the weight distribution was also made proper. And this is with a clear indication of not disturbing the gait pattern as well. So that's a quick note on it. And having done this research, we did happen to go for 2 US patents, and we did hold 2 Indian patents on this custom insole, and a couple of research paper publications on this. And Dr. Shivakumar, he worked along with me on this particular project, wherein he was my PhD student during this research work. So concludingly, all these activities have been achieved. Dynamic and static loading have been considered. The surface area of contact was increased. irregular wear rate was reduced, and customization was done to the core. And when we say customization done to the core, for each and every patient, a separate insole was been printed and it is being given to the patient. So by this, we are saying that it is not that wearing this custom insole will reduce your sugar levels, but it will definitely delay the issues, the foot issues that a person can possibly expect. And when we were doing this particular research, we came to a very clear conclusion, or we saw through different facts, that not only a diabetic patient need to wear a custom foot insole, every one of us need to wear a custom foot insole, because that is where we have our improper load distribution. So that is a bit of idea in terms of diabetic foot insole. The next case study that I would like to discuss is one size does not fit all. Like we all know about surgeries, wherein surgeries are categorized into two types. One is the open surgery and the other one laparoscopic surgery. And open surgery, you open a patient, then the doctors undergo, the surgeons undergo a surgery. And on other hand, in terms of laparoscopy, they use the small probes, and then using these probes, they undergo the surgery. You could see the faces over here. I'll come back to it. Like they do the surgery using probe, and then they say they are good to go, right? The patient is here and they're watching a monitor, and then watching at the monitor, they undergo the surgery. If you look at these two things, like one is the surgeon directly looks at a patient body and then he undergoes the surgery. On other hand, the surgeons, they look at a monitor and then they undergo a surgery, right? And when we started exploring into this particular research, one of our question is, like, let us take a paper and pen and let us directly write over the paper by looking straight at the paper. And next thing, let us look at a mirror and then let us start writing at the paper. Which one do we feel comfortable? Obviously, looking directly and doing the work is the one which gives a better comfort, or that is where it leads a proper information. Whereas in terms of looking at a monitor or looking at a mirror and we writing, or looking at a monitor and we doing the surgeon doing the surgery, there is a certain amount of information which is lost. When we say about the information that is lost, there is a lack of information. Here, the surgeon touches, feels, and senses what he is touching, feeling, and doing. Whereas here, the surgeon doesn't have this much amount of clarity is not left over here, because here the surface, again coming back to it, the surface area of contact that he has is less as compared, he has is very high as compared to what these people have. So that is one thing. When we speak of surface area of contact, like we all know this uh, story. Like the better you have a surface area of contact, the better you will get an information. So the more we expose the surface area, the more the information we can acquire. So that is very clear from this very old story, what we all know. I don't want to go back to the story. So it is very clear from this. And here what is happening is, here the doctor, the only information that he gets is through this laparoscopic device. He gets the information. Like here in the previous case, they touch, they see, and they sense what they are doing. But here they tend to get another sensory information only through the laparoscopic device. They tend to get the feedback. So here we are losing the sense of touch, and information, quite a good amount of information is lost. And this is not the area where we can lose some information, and it is very essential to have enough and more than enough information when it goes to these sort of crucial surgeries. And the communicating device which communicates the information to the surgeon is the laparoscopic scalpel. is the only device which tends to communicate the information. And if you look at this device, this is the common device which is used by all the surgeons who ever undergo it. And the area of contact that they have with this particular surgical equipment is only these two areas, the ring-like profile areas, wherein they put in their fingers, and this is the only communicating device which communicates the patient between the patient, the specific tiny organs to this particular surgeon. If we look at the profile of the surgeon, we have learned about ergonomics in mechanical engineering. So we thought we'll explore a bit more onto it. And if we look at this particular surgical equipment, this remains the same, but the surgeons who are using it have varied hand profiles. Each one has a different hand profile. Like if it is a hefty male surgeon, his finger size is completely different from a lady surgeon, a thin lady surgeon. But all of them, they use only same interactive device. So what we thought is, how can we improve this communication which is getting lost over here? And that is where we went in terms of exploring the surgical errors. And exploring the surgical errors, so many papers we explored on to this, and we found communication error is one of the major problem. And if we go back, if you ask anybody who went through this laparoscopic surgery, 10 out of 6 people will tell you, like after surgery they might have gone thin, they might have gone fat, or they might have having some any other internal bodily issues like continuous bleeding inside their body. So they have some sort of issue that is mainly caused because of the surgical error that had happened during this surgery, and that happened because of a communication lag, because of a sense of touch. And very importantly, there is no measure in order to measure this communication error. We all know that we can logically think and understand that there is a surgical error which have happened over there, or a communication error that have happened over there, but there is no way to measure this particular error. So that is where we thought, how can we use additive manufacturing customization in order to overcome this surgical error that has been experienced by laparoscopic surgeons. So coming back to the surface area of contact, so we already from our foot research, we had a good amount of knowledge in terms of where to use surface area of contact and where not to use surface area of contact. So we went back to the surgical scalpel, and in this scalpel, the surface area of contact is only at these specific four or 5 points, and this area of contact is not enough, because we will know from this story that more the surface area of contact, the better picture or better information we can acquire. But whereas in this case, we don't get that much amount of surface area of contact, so that means that we are getting only lesser amount of information of what we need to get. So then we started using what we studied in ergonomics, understanding different hand profile, measuring the hand profile, and how we can customize things for a specific hand profile. And this, we being dealing with the surgical equipment, we decided we'll take the surgical scalpel that has been widely used now, and we won't do any rework or any modification on the parts that go inside the body. Our maximum concentration is the part which is outside the body, or the external body part is our focus. Nothing which goes inside is our focus. So that is why we decided we start exploring into it. So we removed the part, and as our focus is only on the external one, we decided we'll concentrate on the external part. So this is the existing laparoscopic forceps or laparoscopic scalpel, and this is the area that we decided we are going to work on it. One another reason is, at any point of time, if the surgeon feels they are uncomfortable with the design, whatever we give, all they need to do is, it is just a screw. They can just unscrew this portion and they can fit the regularly used laparoscopic scalpel, and they can carry on with their surgery. So that is where we focused on. That is where the idea was being made to it. So when it comes to design, we came to a design of, we had loads of design which we worked on, and of the loads we came to one of the final design part, which is of this particular profile. That is the place wherein you can put 4 fingers, and this region goes inside the thumb, or it is the region where it goes and gets in contact with the palm. The reason is when we went on with surveys and questionnaires with the surgeons, what they mentioned is when it comes to making more amount of grip, the existing scalpels weren't performing that much grip, or they tend to have an ankle pain when they tend to give a good amount of grip, or they tend to face some issues with that. So that is where, in order to have a good grip, we thought we'll introduce this. On top of it, we want to have a better communication through improving the surface area of contact. And then we 3D printed this part using an FDM printer. And once the part has been printed, we took it for application. So this is the part with actual and the support material. And this is the final clean part. And this is the part that we fixed with the laparoscopic surgical tool. So now we have did customization to some extent. And this is how it would function. Like this goes inside the palm, and this is very crucial thing for navigating. So that is why we gave a separate provision for the thumb, and this gives improved surface area of contact. Wherein in the earlier case, only the thumb and the middle finger were being used for communicating, but here, or for assessing the device, but now the entire hand has been completely utilized for better surgical experience. So this is before and after the surgical equipment. And when we were discussing about this, I specifically mentioned to you that I showed a slide on different hand profiles. And what is that we did for the hand profile? That comes a question. And this is the first state of the equipment. And after this comes the core customization. In core customization, what we do is, let us take, it is going to be a heavy male surgeon. For him, we tend to take a scan of his fingers, and for him, we tend to design one rubber insert for his um, finger profile. And there comes 2 pieces. One is this rubber insert 1, and this rubber insert 2, which goes for the thumb region. So these are the 2 inserts which is specifically designed for him, and this goes to that particular surgeon. And another person, let us say it's a thin female surgeon. For her, we took the hand profile, and for her also we designed one of these insert, one for the thumb. So let us say initially using the same scalpel, the male surgeon goes for surgery. So during that time, all he need to do is he need to insert this inside, and insert this portion in the thumb region, and he need to undergo the surgery. Once he is done, all he need to do is he can remove off, and he can take it with him, and the female surgeon can insert her rubber based rubber inserts inside, and she can perform the operation. So now we gave the customization in terms of the parameters, and specifically for that particular surgeon itself, there is a complete customization that had been undergone. And based on their requirement, we would make it either soft, medium soft, or hard, or whatever will be the way that they feel it is comfortable for them. We vary the show harness, and we print these rubber inserts for one surgeon, and that means that every time and then they can just insert the surgical customized profiles, and they can perform the surgery. So now it is for a better experience and for better surgical data that they can get on. This is particularly towards reducing the communication error that can possibly happen when it comes to laparoscopic surgery. And being engineers, we made sure we undergo all types of scientific analysis. so that the tool stays stable, and we take this tool throughout. Um, so this is the as I mentioned at the very beginning itself, we can't get um, any scientific data on it, and so we gave a quantitative. We can't do a quantitative questionnaire, so it is more of a qualitative, subjective data that we got from the surgeons after using this surgical scalpel. This was before customization, and this was after customization. How they view the tool in terms of grip, functionality, how they feel in terms of comfort, and how they feel in terms of wrist posture. Because in the earlier situation, they had a very tough wrist posture while holding the scalpel, and because of that, they tend to have severe wrist pains after surgery, because usually these surgeries go until minimum it goes for 1.5 hours, and maximum it would go until 6 hours. So that is for that timeline. You can imagine holding a scalpel for such a long time in one particular angle of inclination. So all those been we try the best in order to overcome that issue. So this is in terms of yeah, laparoscopic surgery, and this we came out as a paper, and this got published in Rapid Prototyping Journal. The next one is in terms of dental aligners. We did happen to undergo a research in that as well, and this is one case study that I thought I'll put across. We all know that when there is a dental issue, we tend to go for dental aligners. And if you go back to the dental aligners, these are the very early dental aligners which came into existence in 1000 BC. This came into existence, and we are still more or less following the same technique, wherein in terms of using the braces. Yes, in 1700s there were some efforts which were done in terms of making the braces outside the human face, or outside the tooth, and they failed completely. And then in the early 1900s they came up with the only mechanical method which could be done, that is the steel braces which goes on. And one thing with the braces is it is not so comfortable. Anyone who worn it, like they know how uncomfortable it is to have something in their mouth hanging in for quite a long time. But as we worked with a couple of maxillofacial surgeons and dentists for this particular project, and from their experience, they hadn't moved much in terms of dental um, activity. I mean, dental-based research. Still, the same technology has been used, which has been which came into existence in early 1900s. That is the same thing which has been carried out. Maybe in terms of materials, they improved. There are some slight improvements here and there in terms of putting it, taking it out, but still, this remains one of the very widely used technology. And a couple of disadvantages with that is, uh, as per the maxillofacial surgeons and the dentists, they claim that if a patient wear these dental clips or dental braces for at least 8 hours, a continuous 8 hours in a day, that is more than enough. But we can't keep wearing this, and we can't keep removing these surgical, I mean, these braces for every 8 hours, because it's a tedious process to wear, and it's a tedious process to remove it off as well. So for that reason, what the dentists do is they just put this on and leave it for continuous 15 days, and then they start making the next alignment. So that's how they tend to do it. That is case one. And case two is it becomes hard for cleaning, and while tightening it up, there are situations wherein there would this would lead to some dental cracks. And most importantly, going to the technical perspective from what we discussed with the dentist, let us say that they want to align these four tooths and bring it to this particular state. So initially what they will do is they will start making the alignment from the worst, So this will go in two stages. The worst will be done in two stages. Stage one, for first 15 days, they will push it back. Stage two, again, some more pushing. Stage three, they will make sure while this has been pushed, they make sure there is a gap has been created. So that becomes stage three. And after pushing it, then they start from this tooth. So stage four, they will start from here. They'll take these two tooths as reference, and taking these two tooths as reference, let us say that they want to tilt this to maybe, let us say these two are in roughly about somewhere around 70 degrees. So they want to tilt this to 70 degrees. And after tilting this to 70 degrees, they want to vertically move this by 5 degrees. Okay. Now suddenly I started speaking of degrees. And one interesting thing is when they wanted to tilt this to, let us say, by 70 degrees or align it by a certain degree, 1 or 2 degrees, there is no measure to measure the dental alignments. We have so many technologies which we tend to use for measuring, so many devices that we use across, but this is the region which requires highest precision or highest comfort to a patient or to a person, but there is no measure in order to measure this. So still now it is done on an experience category. So they do it by experience. There is no measure in order to measure this. So because you can't have a reference point in your face, and you from that particular reference point you can't measure anything. So that is why there is a lag which exists in this, and there is no help on this. So then it goes by saying that you need to stick to it. So coming back to this, and keeping these two tooth as a reference, then they align this. And once after aligning this tooth, then it goes for these three tooth would be taken as a reference, and then they align this. So it goes like this until they align the final tooth so that it comes to this particular profile. So literally this takes about 7 stages. So imagine a, a person going to a dentist 7 times. 7 times you add, for safe side, let us have 8 or 9 times. Okay, 9 times a patient visiting the dentist frequently. And one thing is, we know that we don't have the actual data. Whatever the data that we give is of not accurate because there is no measuring device to measure it accurately, number one. And 7 times of visit. So even if for correction, if it takes 1 hour, the patient waiting time, traveling time, each visit would cost him about 4 to 5 hours of traveling and waiting time. So now we are speaking of the amount of time that he spends in terms of visiting the dentist. And still, they don't get the accurate part. Yes, there is a new way of overcoming the braces, what is called as the clear tooth aligners, wherein they use these aligners. And one major advantage of this aligner is a patient can wear this aligner for the same procedure has been done, like 7 stages has been done, whereas when we say 7 stages, 7 different aligners have been produced. Uh, Stage one aligner has been worn for continuous 15 days. And when I say continuous 15 days, the patient wears it during night time or the time when he or she is at home for continuous 8 hours. They need to wear it, and morning they can take it off and they can go ahead with their work. So this is one of the major advantage that have happened in terms of dental aligner. Um, as compared to the previous braces. And though it is said to be an advantage, you know, ice-breaking one in dentistry, but then we went back to see how it has been made. How the dental aligner is made is like you have two molds, one for the bottom portion, bottom line of tooth, and the other for the top layer. So you have a wax mold, and a wax mold has been made. And when you go to a dentist, the dentist puts both these molds inside the mouth with the wax carrying in it, and he asks the patient to press it and hold and sit tight in the same position for 20 minutes. So after 20 minutes, they tend to get an impression, And based on this impression, they take a plaster of Paris mold. So from this negative mold, they make a positive mold. And having this positive mold, this positive mold is again used for making the dental aligner. Okay. What they do is they tend to go for vacuum molding, and using vacuum molding, they tend to make this dental aligner. Fine. One thing over here is you're making a patient to sit idle, holding it for 20 minutes. Our human body is designed in such a way that we can't stand still for more than 20 seconds. Our body will start making a slight move for every 20 seconds because of our nervous system. It will start moving for every 20 seconds. So when we are speaking about a body creating a movement for every 20 seconds, yes, some form of slight movement would be there. So that means that when you're sitting for 20 minutes, you can calculate the amount of movements that you make. So the more the movements that you make, the more clearance it will start creating in this mold. And the more the clearance is, again, that means that we started losing accuracy over here. Okay. And so we'll lose the accuracy over here. And in spite of losing accuracy, for the accuracy which has been lost, they tend to create a negative mold. And for this negative mold, they tend to make the positive mold. And that is where this is what they would do is they take these are biocompatible sheets. Um, Using these biocompatible sheets vary from a thickness of 0.625 mm to 1.2 mm. That is the highest thickness of a sheet, and the lowest thickness is 0.625 mm. And using these sheets, they tend to vacuum mold it, and after vacuum molding it, they tend to get this particular profile. After taking this profile, they tend to cut all these unnecessary portions, and then they tend to put it on the patient. So when they cut all these portions with using the scissor, obviously it will have some sharp edges, and these sharp edges, when it is being put on the mouth, it will start creating a rubbing action over the gums, and it tend to create some gum bleeding, and it is not as comfortable as it is supposed to be. And number two is, again, we have lost the accuracy over here. And if you look at the lead time, a patient visits the doctor by, let us say, by today evening, 7 o'clock, and an impression has been created, and he spends time until 9 o'clock. And when he comes back, and then today morning, the dentist will start doing the negative mold, and from negative mold, they tend to take this mold. And by evening, it takes at least 4 to 5 hours for making this mold. And once it has been done, after 6 hours, this part has been produced, and by today, after 4 o'clock, he or she can go and collect this part, and it is ready to wear. So we are speaking roughly of a timeline of close to about 18 hours for this process to get over. So understanding this, what we did in terms of our work is we took one of the scanners. We took a dental scanner. We quickly scanned the entire portion. The maximum time it took us about 3 minutes to scan the entire tooth set. So once we scan it, after scanning it, now we are speaking of the exact data. There is no missing data over here. We got the exact data, and we cut off unnecessary areas that we don't want to work on. We specifically narrow it down. And after scanning, we take it to Geomagics, and using Geomagics as a tool, we work on this particular project. We specifically pick one area that we want to work on. And earlier I mentioned that there is no measure to measure the dental alignment. Now, if the doctor says that I want to tilt this tooth by 2 degrees, yes, now we are speaking of, we are exactly tilting it by 2 degrees. I want to tilt this by 1.2 degrees. Yes, that is possible because we are using one of the CAD softwares, and obviously we all know that it can be easily done. That has been done over there. And in the earlier case, the patient need to go sit in for 7 stages in order to get one complete profile. But now the patient, if he sits for first 3 minutes, that is more than enough because we got the data in our hand, and every time and then when the dentist want to create a new profile, he sits along with us and we try to make the profile, because we have this data and we know how much we have tilted the earlier tooth, and based on those tooths as reference we start tilting it, and then for this we tend to create those aligners. So once we work along with the dentist, and the dentist is fine with the profile that he wants to tune it, it's all that we do is we create a layer thickness to it. And let us say we want a thickness of 0.625 mm, the same, or 0.8 mm. That can be done. So we just give that layer, because the 3D printing machine that we use for this, it works to an accuracy level of 16 microns, and it is not a tough job for us to get those accuracy levels for this dental application, and we completely get the right custom profile. And in terms of doing this, we also make sure we cut the lines in a very fine arcs so that it doesn't cause any issues to the gums. Whereas in the earlier case, they don't have any idea where the gum regions are and how the profile of the gum region is. But here we can easily see how the gum regions are, and based on that particular profile, we can very finely do the fine cut, and the part is aligner is perfectly made according to it. And the aligner that has been made, it is printed through 3D printing, and the maximum time it takes for alignment and 3D printing together along with post processing, not more than 2.5 hours, a part has been made ready. And this is the part which is being 3D printed, and the part along with the support material, and these two combinations are taken, and the support materials are removed. And once after removing the support structures, this is the aligner which is quite ready, and we tend to just ship it off to the patient. And this, we came out with a publication on this as well, um, on the particular activity. So that is on the dental side what we worked on, and that is one of the, again, that is the third live application that we did in terms of it. And I know that we are running about 15 minutes. We have 15 to 18 minutes. I can pick one case study. I will leave it to your choice. I can discuss on orthotics or on a case study on prosthesis to a peacock. I'll give the audience a choice. You can pick one of the case studies. I'll go to that particular case study. One is on clubfoot, how we worked on orthotics, and the other one is how we worked on orthotics for a peacock. Anybody else? Which one would you like to pick?
Sir, good evening, sir. This is Prabhu from Saram Engineering College.
Yes, sir.
How are you, sir?
I'm doing good, sir. Perfectly good. How are you?
Sir, I'm fine, sir. Sir, what about the peacock case study, sir?
Sure, sir. I'll go to peacock one. Right. This is on a case study on peacock. Like, this was quite a very interesting thing. And it so happened one day I took my son to a local zoo in Coimbatore, and there we saw one of this peacock with an amputated limb. And he asked me, like, you say that you do this and that for humans. Why don't you give a prosthetic leg? Why don't you give a leg for this peacock? Can you give a try with that? So that is why we started this particular project. And in this particular case, this is a peacock which we worked on, and the peacock had a limb which got amputated, and we decided we are going to put an artificial limb to this. So that is where we started. And from our dental story, we know, and this is the actual limb, and to this actual limb only, we need to fit the artificial limb. So this region is the interfacing device or interfacing region between the actual and the artificial. So we need to make sure this interface data is there with us, so that we need to create this interfacing device. And from dental side, we are very clear, like how to take a negative mold, how to take positive mold. We know all the stories. So the same thing we did for the peacock. So we took a plaster of Paris mold. We took an impression of the peacock amputated limb portion, from ideally from the negative mold, create a positive mold, and yes, we had using plaster of Paris, we created this profile, which is the interfacing device, or which is the profile of the actual limb. And to this is what we need to put the artificial limb. So our interfacing area is fine. And once we have this, we know the story, we can scan it and I can put it in Geomagics. And as how we saw in dental, all I need to do is once we have in Geomagics for any profile that I have, um, fine tune the profile. All I need to do is giving a thickness layer. There we worked on a thickness layer of 0.625 to 1.2 mm, and now working at a thickness layer of 3 mm is not a tough job. So all we did is give a thickness layer. We created this profile, and after creating the profile, all we did is go for a 3D printing FDM print, and we had the print, right? So until this, we are very clear. And when we went for this particular project itself, during the time itself, we were very clear. Yes, we know so many electronic gadgets are there. We know pneumatics is there, hydraulics is there, everything is there. But we decided we are not going to use any of the electronics, hydraulics, or pneumatics. It is only going to be very simple mechanics, and we are going to limit the entire product, entire artificial limb within 5 components. Our maximum line should be 5 components, or anything that we work is going to be less than 5. So that is why we started creating our own building blocks, and we that is why we started working on this. So it is very clear, maximum components can be only 5. No pneumatics, hydraulics, electronics, only simple mechanics. And very importantly, we also decided we need to have this interface device, and this peacock will go under different atmospheric conditions, and we can't put a fastener. We don't want to have any loose moving parts. Yes, we can say that we can put a stainless steel screw to connect it, but we decided we are not going to use any screws or any Allen keys or screws in order to make the interaction. The reason is, if the peacock is in trouble, we want the zookeeper by himself to remove it off immediately, to remove the artificial limb from the peacock immediately, because when we put any screws, then he need to go in search of those particular screwdrivers or spanners or whatever it is. And every one of us will have a quick access to one of the sharpest blades or anything that is sharp. So we decided, using a very common thing, we need to remove it off. So that is where we decided, or we brainstormed, that is where we are going to stick to it. So now we are clear with our borders. And as you saw through the diabetic foot insole, we are very clear with static loading, dynamic loading. Yes, the peacock walks, runs, and yes, now we came to a new challenge, that is the peacock also flies. So when it flies and lands, we need to make sure the product that we are designing, it should also take the load when it flies and drops. And we very well know that anything that drops from height of 7 meters, the load is going to be quite very high, because the average weight of a peacock starts from, this particular peacock weighed about 6.8 kilos. And we can imagine a load which is falling from 6.8 kilos from a height of 7 meters, it is going to be quite very heavy. So we need to design it in such a way that load is being taken. And we were very clear, not more than 5 components. And still we need to achieve all these things. And again, whether the product shouldn't get rusted, it shouldn't, there shouldn't be any maintenance at all at any cost. So that is where we decided we need to work on. So these are the parameters that we considered, and I'll come back to this. And there came yet another new challenge for us. How are we going to find the weight of the other limb? Like, this limb is there, and how are we going to assess what would be the weight of the other limb? And we can't weigh this limb alone. And this is the time that we realized that we went through most of this anatomy based software, most of the engineering software, and no software gives a data wherein if you put the bone density, or if you put the muscle texture, and if you put the water content, no software in the world gives what is the weight of that particular organ would be. That was one challenging thing. And we can't add too much weight. We can't have lesser amount of weight. Any change with the weight, the peacock will start feeling uncomfortable. So we need to have the right weight to be placed over here, and that became one of the major challenge. And another challenge was, like we mentioned about the static and dynamic loading. And in terms of human beings, yes, I made a patient to walk on the EMET pressure sensor, and I took the pressure distribution. But here, I don't know what is the walk per minute of the peacock. So, because this peacock is limping, so we need to understand what is the walks per minute that this peacock undergoes, so that we need to give the spring back calculation, because we need to give at what rate this peacock limb, artificial limb, need to get spring back. That we can do only if we know what is the mm, weight of the artificial limb that is going to go. And second thing, the walks per minute, the velocity in which it is moving. So all these things became, I would say, those were really fantastic challenges for us. And you won't believe the amount of time that we spent on this was way higher than any other research that I did until now. But we came out with good results at last. So these were quite very challenging things, and we didn't get any information for this. And all we need to do is, then we came to a conclusion that the weight of this part can't be more than 450 grams. Sorry, 420 grams was the maximum weight, permissible weight that we can add to it. Anything more than that, the peacock would start feeling uncomfortable. Anything less than that, the peacock also started feeling uncomfortable. Because how we came to this weight conclusion is, we started adding and removing of weights. We made so many prototypes of this particular part, and then we started coming out to this weight calculation, because we couldn't measure that by any other means. And the reason for these pores are nothing but, in one is for weight reduction, and second thing is, the more the porosity is, the skin breathing would be better. So that is one reason why this interfacing device was given much of the holes. And this is the final design that we came out with. So it has 1, 2, 3, and this entire part falls as one single thing, and then there is a spring which goes in. And I'll show you the connecting device. This is the final end part that we came out with. So it only has one, this part, the other end two. This is the third part. This is one full complete assembly, and then the spring which goes on. So that's how we narrow down this. And this, the way how we connected us, we all know these electric tags. You have these when they tie two wires. These are nothing but the electric tags commercially available for 50 paise, I think. And all you need to do is you just insert it, you pull it up, it gets locked. And when you want to remove it off, all you need to do is you just take a blade, you cut it off, that's all. Just by two cuts, the entire device has been cut off from the peacock. And another thing, another interesting challenge that we faced was, we did all these things. The spring back calculation was done based on the walks per minute, averaging of walks per minute, and we came to all these things. And what would be this profile? That came to your question. We made at least 50 different types of profile combinations, and then we got this design from Paralympics. The reason is, we can't have any protruding part, because when the peacock lies and wakes, it will start scratching the feather or the body. So it need to be so soft that it doesn't cause any harm, or it doesn't get stuck inside the feather or feather. So that is one essential thing. And another thing is, when it tends to fly and when it jumps down, it need to take the spring back. So that is why we gave this design which we took from the Paralympic Olympic athletes. The same design was used so that it gives a spring back of its own, and it does the functionality. So this is the final end version of the entire design, and this final end version is the one that we fitted to the Peacock. And I just inquired a couple of months before. This project was completed maybe way 9-10 months before, and still I heard the Peacock is using the same prosthetic limb, and it is still in Kanto Zoo. So this was one of the very challenging research work that we did, and finally we went for a publication on this as well. So that's about different case studies that we went through. And not only this, I'll give you a quick look on. We did a project for people who are with clubfoot, that is people who have foot like this. The traditional method is Ponseti method. From this method, we came up with a novel idea wherein we worked on a case study for this kid. The existing market available ones, they need to have two limbs in order to do the correction. But we came up with a solution for this particular kid. He has only one limb, and for this kid, we gave a prosthetic limb for the other leg, and while we gave a correction limb for this particular limb, and we came out with one of our novel designs of this part, and then we used it for application. And this does all the 6 degrees of freedom of action in our leg, and this we went as a publication in rapid prototyping journal as well. And one final thing is in terms of bed ulcers. Like at the moment, we know how the ulcers tend to act, and in the diabetic foot, the foot area region is very less, and that we tend to have worked on dynamic static and dynamic loading. That is when a person stands and when a person walks. How we analyzed for that situation, because again there is a pressure ulcer. The same pressure ulcer, it happens when a patient lies in the bed because of the shear and the friction forces, and we try to understand this particular situation. And the existing methods are fluid, water, and the foam beds are the ones, but these are not completely customized, and these doesn't have air ports as well. So because of moisture, it tends to aggravate. And then we, for this situation also, we came out with a novel bed. Um, Ideally, it is for us, it is nothing but what we worked in foot project, we expanded to the whole body, and we made the pressure distribution to be evenly spreaded. And by doing that, we spreaded the pressure points, and the bed completely customizes itself according to the movement of the patient. If the patient lies on the other side, lies like this, the bed profile completely changes. And when the person turns towards the left, or person turns towards the right, or person lies facing down, under each and every circumstance, or when he sits, or when he lies like this in the bed, every time the bed will change its profile according to this human body. So that is, and it tends to take the pressure distribution. So that is what we came out as a novel solution, and we did happen to get 2 patents again on this, and one of our patent is pretty much available. And I'd like to share my acknowledgement to my fellow researchers who worked with me on these projects. And I thank you for your time, and I'm pretty much open for questions. Sorry if I was rushing a bit, but I want to stick to the timing. So I want to complete things by time. So I just finished it. Thank you. Thanks for your patient listening. I'm pretty much open for questions.
Anyone? So thank you, sir. This is Prabhu, sir.
Yes, sir.
Sir, it has been a good listening to your lecture after 10 years, sir. Actually, it's a very good experience for me.
Thank you, sir.
Looking forward for some more sessions forward, sir. Thank you.
Thank you, Prabhu.